Hi, so welcome to the video lecture for the t-test for the mean. This is also called the one sample t-test. So the one sample t-test is similar to the z-test for the mean that we did last week. So just like when we had the t confidence interval and the z confidence interval, we have the t-test and the z-test. And just like with the t confidence interval, we used that when we didn't know the population standard deviation. And we'll do the same thing here. When we don't know the population standard deviation, we use the t-test instead of the z-test. So we're using the sample standard deviation instead of the population standard deviation. So to use this test, just like with the confidence interval for t, we need to know that either we have a large sample size or we're sampling from a normal distribution. Most of the time, I'll just tell you to assume a normal distribution in the problem. But if you have data, you could look at a histogram to see if it looks like it's normally distributed. So we've got, just like before with the z-test, we've got three possible sets of hypotheses. For all of these, the null hypothesis is mu equals some hypothesized value, which we're calling mu naught. The alternative hypothesis could be mu less than the hypothesized value, it could be greater than, or it could be not equal to. And just to remind you, because this comes up with SPSS, and it's really important with SPSS, this not equal to option is called the two-tailed test, and the less than and greater than ones are called one-tailed tests. So for the t-test, the test statistic is calculated almost exactly the same way we did with the z, and we'd get the p-value the same way, just with a t distribution as opposed to a z distribution. However, for us, we're just going to get the test statistic and p-value from StatCrunch or for SPSS. So let's start with an example. So in this example, an office manager has 25 workers and is monitoring how much time they spend off task on Facebook or whatever. And so we've got the sample mean is 65 minutes with a standard deviation of 17 minutes. And I want to point out here this standard deviation, because of the way this is phrased, the sample mean is 65 minutes with a standard deviation of 17 minutes. That 17 minutes comes from the sample. And so that makes this a t-test instead of a z-test. And so in this question we want to know, does the mean exceed 1 hour? So we go over to StatCrunch. And we just go to Stat, t-stats, one sample with summary, because they've given us the summary statistics here. We have a sample mean of 65 minutes, a sample standard deviation of 17 minutes, and that's based on a sample of size 25. Our hypothesized value is 60, and we want to know if mu is greater than 60. So we enter all that and hit compute, and this is our output, and you're just going to copy all that and paste it into your homework, just like I've done over here. So in the output, it gives us the hypotheses, the test statistic, and the p-value. We still need to state the rejection rule and the conclusion. So the rejection rule is reject H naught if p-value is less than alpha, the alpha given in the problem, 0.1. The rejection rule, no matter what hypothesis test we're doing, is always going to be the same. It's always going to be reject H naught if p-value is less than alpha. So here, our p-value is less than alpha, so we're going to reject H naught and say that that means there is sufficient evidence to conclude that mu is greater than 60 minutes. Okay, so that's our first example. For our second example, let's look at when you've got data instead of summary statistics given. So in this example, a psychologist has given a bunch of people a test where they're asked to push a button when you think 7 seconds have passed. And these are the actual lengths of time that they picked. And we want to know, is there sufficient evidence to conclude that they're estimating these, that their estimates are off, that they're different from 7 seconds. And so that would be less than or greater than 7 seconds either way. So if we go to StatCrunch, I've typed the data in already. We go to T-Stats again, one sample, and this time with data instead of with the summary. So we pick our variable, and our hypothesized value is 7 minutes, and we wanted that to be not equal to anyway, so we'll leave that there. Hit compute, and that gives us the hypotheses, gives us a test statistic, and it gives us a p-value. So you'll copy that and paste it into your homework, and then we still need to state the rejection rule, which is reject H0 if p-value is less than 0.01, was given in this problem. And that tells us that we fail to reject H0 because this p-value is not less than 0.01. So there's not sufficient evidence to conclude that mu differs from 7 minutes. So we can't say that their estimates are incorrect. All right, so that's how to do those problems. Let's talk now about effect size. So every hypothesis test that we're going to do has an effect size to go with it. There's a statistician named Jacob Cohen came up with effect size formulas for each of the hypothesis tests that we're going to cover. And I like covering them because they're easy to calculate and they're easy to interpret. The benefit of doing effect size is that so far the hypothesis tests that we've done, the conclusions are only yes or no. Have we supported this claim or not? Effect size is a way of getting at a little more nuanced result. And another reason for doing effect size is, if you notice, for a large enough sample, anything will be significant. Any small difference between x bar and mu will turn out to be reject H0. Effect size takes the sample size out of the equation. So we'll look at that. So Cohen gave these, back to this, Cohen gave rough guidelines for each test. We're going to have a measure of effect size. For each one of those, we're going to have rough guidelines for what's small, moderate, and large effects. Cohen made a big deal, though, about saying that these are really rough guidelines and that you should always consider your results in the context of the problem, and you should always compare to other research in the field. So if you're doing research on a certain thing, you should look and see what other research has been done on that thing to see what the effect sizes were there, to have something to compare to. So let's look at the one sample t-test. So the effect size is, that's not showing up very well, but that's an x bar here. So it's called Cohen's d. It's the absolute value of x bar minus the hypothesized value divided by the standard deviation. So you just take x bar, subtract the hypothesized value, take the absolute value of it, which just means if it's positive, leave it alone. If it's negative, drop off the negative sign, and then divide by the standard deviation. And the rough guidelines he gave were that quantity, if it's 0.2 is small, 0.5 is moderate, 0.8 is large. If it's somewhere in between, you could call it, small to moderate, you could call it small-ish, you could call it whatever seems reasonable, whatever seems reasonable. So if we look at our first example, or example 1, from earlier in this video, we said that the sample mean was 65 minutes with a standard deviation of 17 minutes, and we were comparing that to 1 hour. So to plug that in, x bar is 65 minus our hypothesized value, which was 60. So we did 65 minus 60, make sure it's positive, and then divide by the standard deviation of 17 minutes. So that gives us 0.2941, which is between small and moderate, so I just called it fairly small. Okay, so for this one, we were able to reject the null hypothesis. So it looks like we can conclude that the mean time exceeds 1 hour. It just doesn't exceed it by a whole lot. So from the second example, for this example, I went and ran the summary statistics. So I just ran summary stats, and got the mean and standard deviation. Okay, so we need the mean and standard deviation to do this calculation. So we do that and just plug in here. The mean is 7.01. Subtract the hypothesized value of 7. Make sure it's positive, and then divide by 0.0316. Well, that's 0.3165, which is still in the small to moderate range. All right, so that's the effect size. And now let's look next at SPSS. So in SPSS, so I've got an SPSS file here, and we're going to use this for our examples here. We've got variables here having to do with attention span, the amount of time people spend, this is all for teenagers, on household chores in a week, how much time they spend watching TV per week, exercising per week, and then we've got some other variables. So if here I wanted to test whether the mean number of hours per week differs from 10 hours. So we're going to analyze, compare means. This is a one sample t-test. So analyze, compare means, one sample t-test. And we've got the number of hours spent watching TV, so we're going to move that into the test variable box. Our test value, we said we were wanting to compare it to 10 hours per week. So we'll click OK, and that's how we get this output that you see over here. So it gives you the sample statistics, and it gives you this T here is the test statistic. Now the sig two-tailed, that's the p-value if your hypothesized value, or if your alternative hypothesis is not equal to. Okay, so it tells you this is sig, this is the significance value, that's the p-value, if your test is two-tailed. So if the hypothesis test you want to run is not equal to, then that's your test statistic and p-value. And you can just write all this down from there. So you've got your hypotheses, your test statistic, your p-value, your rejection rule, and then your conclusion. If the hypothesis test you want to run is one-tailed, then the only difference is you take the sig two-tailed and divide it by 2. Okay, so if you want to run a one-tailed, you take the two-tailed, divide it by 2. So the only thing different here is our alternative hypothesis is less than. The test statistic is the same, but the p-value is divided by 2. which in this case happens to yield the same conclusion, the same result. All right, and then to get the effect size, we just use the statistics up here. All right. So that's it for this lesson.